Like clockwork, every 22 minutes for the past 35 years, a signal has pierced the silence of space and reached Earth. It's not a satellite or any man-made object. It's a signal from deep space, which is a mystery. Scientists call it GPM J1839-10, but its origin remains mysterious. Is it a message, a phenomenon, or a clue to something bigger? The signal captured by one of Earth's most powerful telescopes has become the subject of global curiosity and debate. Where could it be coming from? And why should we care? Today we'll delve into a cosmic detective story that challenges our understanding of the universe itself. Let's get started. So how can we tune in to unlock the secrets of such a signal? The tool that makes our space exploration possible is radio astronomy. The story begins in the 1930s when American physicist Carl Jansky was researching radio interference. What he discovered was unexpected: radio waves emanating from the Milky Way. This accidental discovery marked the beginning of radio astronomy. Unlike traditional astronomy, which relies on visible light, radio astronomy listens to the universe. It tunes to frequencies inaccessible to the human eye, revealing celestial phenomena that would otherwise remain hidden. Since its inception, radio astronomy has undergone a technological revolution. Today's radio telescopes are marvels of engineering, capable of picking up signals from unfathomable distances. In the remote outback of Western Australia sits a space detective unlike any other, the Murchison Broadband Array. It's not just a telescope. It's a sophisticated network designed to explore the farthest reaches of the universe. Composed of thousands of antennas scattered across an arid landscape, the Murchison Widefield Array is an engineering feat and a testament to human curiosity. Each antenna is like a finely tuned ear listening intently to a whisper. Behind the scenes, a team of dedicated scientists and engineers work tirelessly to calibrate and maintain this complex system. What's their goal? To pick up signals over a wide range of frequencies. This is crucial for studying different celestial phenomena, as each emits its own unique radio signature. Once captured, these signals are processed in a state-of-the-art data center. Here, powerful algorithms sift through the cosmic noise to identify patterns and anomalies, turning raw data into valuable scientific discoveries. Among the array's most intriguing catches are fast radio bursts, or FRB. These high-energy phenomena are incredibly brief, lasting only milliseconds, yet emit as much energy as the sun emits in nearly a century. It was in this cosmic cacophony that our mysterious GPM J1839-10 signal was discovered. Unlike other signals, this one has a rhythmic pattern and has been arriving at Earth every 22 minutes for the past 35 years. What sets this signal apart is its consistency and longevity. While most cosmic signals are random or short-lived, this one's proven to be both stable and constant, making it a subject of intense study and debate. So unlike time signals that come and go, GPM J1839-10 arrive continuously every 22 minutes without fail. Its rhythmic pattern is unlike anything we've encountered in the field of radio astronomy. For 35 years, it's maintained this cycle, challenging our understanding of cosmic phenomena. The initial discovery was met with skepticism. Could it be an artifact or some kind of interference? Rigorous checks were made, and yet the signal persisted. Subsequent observations only confirmed its existence, making it one of the most enduring mysteries of radio astronomy. So what makes GPM J1839-10 different from other cosmic signals? Most signals from celestial bodies such as pulsars and magnetars are either sporadic or have different intervals, but not this one. Its 22-minute periodicity is like a metronome in a vast orchestra of cosmic signals, a rhythmic constant in a sea of variables. Further analysis reveals even more peculiarities. The waveform does not follow the typical profiles of known celestial radio emissions. Its frequency and amplitude have nuances that have yet to be fully understood, complicating an already confusing mystery. Many theories have been proposed, from rotating neutron stars to strongly magnetic magnetars, as well as even more exotic theories like the interaction between double black holes. However, none of them meet all the requirements perfectly, and that leaves the scientific community in a state of intrigued bewilderment. When it comes to mysterious radio signals from space, suspicion often falls on pulsars. These celestial beacons are known to emit beams of radio waves, making them prime candidates for any unexplained cosmic chatter. But what are pulsars? Pulsars are neutron stars born from the remnants of massive stars that have become supernovae. They spin at incredible speeds. When they spin, their magnetic fields generate beams of electromagnetic radiation, including radio waves. These rays sweep through space like the beams of a lighthouse on the sea. When these rays cross the Earth, our radio telescopes pick them up as pulses, hence the name pulsars. The signals from pulsars are usually quite regular, often with millisecond accuracy. This predictability has even led to the use of some pulsars as space clocks to aid in tasks such as spacecraft navigation. So, could GPM J1839-10 be a pulsar? At first glance, one might think so, given its rhythmic 22-minute interval. However, if you dig deeper, the differences become obvious. Unlike typical pulsar signals, which have a constant shape and amplitude, GPM J1839-10 exhibits features that set it apart from others. Its waveform does not follow the profiles we usually associate with pulsars, and its amplitude exhibits variations that have yet to be explained. Moreover, the longevity and permanence of the signal contradict what we know about pulsars. These celestial objects can slow down over time due to a loss of rotational energy, which would affect the timing of the signals they emit. Nevertheless, GPM J1839-10 has remained unchanged for more than 3 decades. To summarize, although pulsars are often the culprit behind mysterious radio signals, this time they seem to have been left innocent. While pulsars are often the first names on the list when it comes to cosmic radio signals, magnetars round out that very list. Magnetars are neutron stars that don't quite fit the pattern, with magnetic fields so strong they defy comprehension. To understand the magnitude of a magnetar's magnetic field, consider this. It is about 2 quadrillion times stronger than Earth's magnetic field and 20 trillion times more powerful than a refrigerator magnet. These are magnetic fields so strong they can erase data from a credit card halfway to the sun. Magnetars are known for their bizarre properties. They emit X-rays and gamma rays, but can also produce radio emissions. These emissions are often associated with stellar earthquakes, seismic events on the surface of a magnetar that release enormous amounts of energy. Imagine an earthquake, but on a cosmic scale. These stellar earthquakes can distort the magnetic field of the magnetar, causing the release of energy in the form of electromagnetic radiation, including radio waves. So, could a magnetar be the source of our mysterious GPM J1839-10 signal? Well, at first glance, it might seem plausible. After all, magnetars are known for their strange behavior. However, the concept of starburst fails to explain the constant 22-minute signal interval and its longevity. Starbursts are sporadic events, and their emissions will not have this rhythmic, clock-like precision of GPM J1839-10. Moreover, starbursts tend to change the magnetar's rotation period and magnetic field with time, which is not consistent with the unwavering consistency of our enigmatic signal. Despite their bizarre and extreme properties, magnetars are not the key to solving the mystery of GPM J1839-10. While they offer an intriguing possibility, the evidence, or lack thereof, takes us back to the drawing board in search of a better explanation. As we continue to explore astrophysics theories regarding GPM J1839-10, we come up with hypotheses that, while less common, offer tantalizing possibilities for the source of this enigmatic signal. First on the list is the white dwarf hypothesis. White dwarfs are the remnants of stars that have exhausted their nuclear fuel. They're incredibly dense and have strong magnetic fields and can theoretically cause radio emissions. Could a white dwarf be the signal emitter behind GPM J1839-10? Again, while the theory is intriguing, it faces problems. White dwarfs do not typically emit radio waves with the same level of consistency and periodicity as our enigmatic signal. Moreover, their magnetic fields, although strong, do not exactly match the features observed in GPM J1839-10. Another frontier theory leads us to the dynamic interactions between stars and exoplanets orbiting them. In this cosmic dance, the magnetic fields of the star and exoplanets can interact in ways that do produce unique radio emissions. While this theory offers a fascinating avenue of investigation, it also comes with its own challenges. Such interactions will likely produce a wide range of signals rather than the unwavering 22-minute cycle we observe with GPM J1839-10. Now finally, let's look at double brown dwarfs, objects on the boundary between planets and stars. When two such brown dwarfs orbit around each other, their magnetic fields can interact, potentially emitting radio waves. Now again, while this theory breaks new ground, it's not fully consistent with the data we have. Magnetic interactions between double brown dwarfs are likely to produce a more chaotic signal rather than this rhythmic, clock-like pulse of GPM J1839-10. As we continue to unravel the mystery of GPM J1839-10, a new perspective is emerging that takes into account the environment in which the signal exists. Could surrounding cosmic debris and stellar winds influence the signal patterns we observe? Imagine a radio signal traveling through space and encountering asteroids, gas clouds, and streams of charged particles along the way. These environmental factors can act as space filters, changing the characteristics of the signal by the time it reaches Earth. The idea is not purely speculative. Studies have shown that space debris can indeed affect the properties of radio signals, causing changes in amplitude and even frequency. But is this a case with GPM J1839-10? Stellar wind, streams of charged particles emitted by stars, that's another environmental factor to consider. These winds can interact with the radio signal, causing it to oscillate in ways that may explain some features of GPM J1839-10. Interestingly, the results of fast radio burst 201-809-16b offer some parallels. This particular FRB exhibited patterns that were puzzling at first but were later found to be influenced by the local environment, including the presence of a nearby magnetar and the surrounding cosmic plasma. Could a similar environmental influence occur with GPM J1839-10? Although the contexts are different, the idea that local space conditions can affect the radio signal adds another layer of complexity to our understanding. As we approach the final frontier of this study, it's time to consider the broader implications of this enigmatic signal and what the future holds for its study. Fortunately, the source of GPM J1839-10 remains active, its signal still traveling through the vast cosmos to reach us here on Earth. This opens the door for anyone around the world with the right tools to observe it, adding their own notes to this cosmic symphony of discovery. Dr. N. Hurley Walker, standing at the helm of previous research, and her colleagues are already on the case, planning to continue their observations as well as examine archival images in search of similar phenomena in the Milky Way. Their ongoing efforts are aimed at solving this mystery, and their initial results are promising. The discovery of GPM J1839-10 has confirmed that ultra-long period radio sources are not as rare as previously thought. This suggests that upcoming studies in the galactic plane may reveal even more examples, expanding our understanding of these enigmatic signals.